In this scene, we'll review the key properties of cyclic quadrilaterals that are essential for solving this problem. A cyclic quadrilateral is simply a four-sided figure whose vertices all lie on a single circle. You'll be able to apply the converse of the cyclic quadrilateral theorem to solve geometric problems. Consider the quadrilateral PQRS. If this quadrilateral is cyclic, meaning its vertices P, Q, R, and S lie on a circle, then its opposite angles must be supplementary. This means that the measure of angle P plus the measure of angle R equals 180 degrees, and the measure of angle Q plus the measure of angle S also equals 180 degrees. The opposite angles add up to 180 degrees. Now, the converse of this theorem is equally important. The converse says that if you have a quadrilateral whose opposite angles are supplementary, then that quadrilateral must be cyclic. Its four vertices must lie on some circle. So, to prove that our intersection point lies on the circumcircle of triangle ABC, our strategy will be to prove that the quadrilateral formed by points B, C, D, and the intersection point is cyclic. Or, equivalently, the quadrilateral formed by C, A, E, and the intersection point is cyclic. If we can show the opposite angles add to 180, we're done. Alternatively, we can use an exterior angle property. A quadrilateral is cyclic if and only if its exterior angle is equal to the interior opposite angle. In this example, if the exterior angle at vertex S equals the interior angle at vertex P, the quadrilateral is cyclic. This is a very useful criterion for our proof. By the end of this scene, you've seen the properties of cyclic quadrilaterals. Now let's return to our problem and apply these ideas. Welcome back to the problem. In this scene, we will define a crucial point that will simplify our analysis: the center of the spiral similarity. Our goal here is to identify a specific geometric point that connects the triangles involved in this problem. Recall the condition from the problem statement: angle BAD is equal to angle CAE. Let's call this common angle alpha. This means angle BAD equals alpha and angle CAE equals alpha. Let's add the angle CAD to both sides. Notice that CAD is a common angle to both triangles ABD and ACE. By adding the common angle CAD to both equal angles, we get two new larger angles. The first side becomes angle BAC. The second side becomes angle EAD. Therefore, we've shown that angle BAC is equal to angle EAD. Now, consider triangle ABD and triangle ACE. They both share vertex A, and we know that angle BAD equals angle CAE. Let's construct a point, let's call it P, that will become our center of spiral similarity. Let P be the intersection of the circumcircles of triangle ACD and triangle ABE. This point P is the center of a rotation and scaling that maps segment PC to PD and PB to PE. Because P lies on the circumcircle of ABE, it has a special property related to its angles. The key property is that any point P on the circumcircle of a triangle ABC will form the same angle with any two vertices A and B as the angle CAB. Let's see how this helps us in the next scene. We have identified a special point P. In this scene, we will use its properties to show that it is the center of a spiral similarity. Our goal is to demonstrate how P acts as a pivot, rotating and scaling one triangle to another. Let's bring back our diagram with triangle ABC, the points D and E, and our special point P, which lies on the circumcircles of triangles ABE and ACD. First, let's use the fact that P lies on the circumcircle of ABE. In cyclic quadrilateral APBE, the exterior angle, angle PEC, is equal to the interior opposite angle, angle PAB. Remember, angle PAB is the same as angle DAB, so angle PEC is equal to angle DAB. Next, let's use the fact that P lies on the circumcircle of ACD. In cyclic quadrilateral PCAD, the exterior angle, angle PDB, is equal to the interior opposite angle, angle PAC. Similarly, angle PAC is the same as angle EAC. So, angle PDB is equal to angle EAC. We are given that angle BAD equals angle CAE. This tells us that the exterior angle at E, angle PEC, is equal to the exterior angle at D, angle PDB. Now let's consider the angles at our center P. In cyclic quadrilateral APBE, angle APB subtends the arc AB. In triangle PCE, angle PCE is exterior to the triangle, so it's the sum of the remote interior angles, angle CPE, and angle PEC. This gives us a relationship between the angles around P. We now have enough information to confirm that P is the center of a spiral similarity. We've established that the exterior angles at D and E are equal. In this scene, we will show that point P is equidistant from lines BE and CD. Our objective is to prove that the distance from P to the Sevian BE is the same as the distance from P to the Sevian CD. Draw perpendiculars from P to the lines BE and CD. Let's call the foot of the perpendicular from P to BE as Q, and the foot of the perpendicular from P to CD as R. We want to show that the length of PQ is equal to the length of PR. Consider the angles at vertex P. In cyclic quadrilateral PCAD, the angle PCD subtends arc PD. The angle PAD subtends arc PD. Similarly, in cyclic quadrilateral PBEA, the angle PBE subtends arc PE. The angle PAE subtends arc PE. Since the given condition is that angle PAD equals angle PAE, it follows that the angle subtended by PE is equal to the angle subtended by PE. Now we can look at the angles PBE and PCD. Angle PBE is equal to angle PAE, and angle PCD is equal to angle PAD. Since PAE equals PAD, it means angle PBE equals angle PCD. This is a crucial step. Now, let's consider the right triangles PQB and PRC. Both are right-angled triangles. We've just shown that angle QBP equals angle RCP. Since we have a right angle and one other angle that are equal, the third angles must also be equal. This means triangle PQB is similar to triangle PRC. Furthermore, because the angles are equal and the arcs PD and PE are equal, the chords PD and PE must have the same length. This gives us another pair of corresponding equal parts. We have two similar triangles with a pair of equal corresponding sides. This means the triangles are congruent. Therefore, triangle PQB is congruent to triangle PRC by angle side angle. And since they are congruent, their corresponding sides must be equal. This proves that PQ equals PR. We have now proven that the point P is equidistant from the lines BE and CD. In the next scene, we will use this fact to complete our proof. We've built up to this point. In this final scene, we'll use the fact that P is equidistant from BE and CD to prove it lies on the circumcircle of triangle ABC. The learning objective for this scene is to conclude the proof by connecting the equidistant property to the condition for a cyclic quadrilateral. Let's assume, for the sake of contradiction, that the intersection point of BE and CD is not our point P. Let's call the actual intersection point S. We know from the previous scene that P is equidistant from the lines BE and CD. This equidistant property is the defining characteristic of a point on the angle bisector. Specifically, the set of all points that are equidistant from two lines forms the angle bisector of the angle between those two lines. In this case, the lines are BE and CD, and the point S is their intersection. So, P must lie on the angle bisector of angle BSC. This means that the line segment PS must bisect the angle BSC. In other words, angle PSB equals angle PSC. Now let's use our cyclic quadrilateral properties. Because P lies on the circumcircle of triangle ACD, the quadrilateral PCSD is cyclic. Its opposite angles are supplementary. So angle CPS plus angle CDS must equal 180 degrees. Similarly, because P lies on the circumcircle of triangle ABE, the quadrilateral PBSE is also cyclic. Therefore, angle BPS plus angle BES must equal 180 degrees. We've shown that angle PSB equals angle PSC. We also know that the angle S is shared. The sum of the angles around S is 180. The only way this setup is possible is if S and P are the same point. This means our original assumption was incorrect. The intersection of BE and CD is the point P. Now we can conclude the proof. We have proven that the intersection point P lies on the circumcircle of ABE and the circumcircle of ACD. Both of these circles pass through point A. A theorem states that if two circles pass through points P and A, then all points in the intersection of those circles must be on the circumcircle of triangle ABP. In fact, P and A define a unique circle containing B and C. This proves that P, and therefore the intersection of BE and CD, lies on the circumcircle of triangle ABC. Let's recap. We started with a specific angle condition. We used properties of cyclic quadrilaterals and spiral similarity to define a point P. We proved that P is the center of a spiral similarity and that it is equidistant from the Sevians. This led us to conclude that P must be the intersection of the Sevians and that this intersection point lies on the circumcircle of the original triangle. And with that, the proof is complete.